Hello everyone, welcome back to the week 10 of NPTEL TA Live interaction session. So for the Rapid Manufacturing course, the course ID for this course is noc22-me74 and this is Palkin Gupta, PhD scholar and a PMRF scholar in Department of Material Science and Engineering, IIT Kanpur. The course instructors for this course are Professor J. Ram Kumar and Professor Amandeep Singh, Department of Mechanical Engineering, IIT Kanpur. So, I think all of you are maintaining the enthusiasm as this course is nearing its end, and I hope all of you have gone through this week's content. So, we'll be covering the important topics from this week very briefly, and then we'll be solving some sample problems, so as to help you understand this week's assignment. All right. Okay. So in this week's lecture, we had majorly studied about the post-processing concerns for rapid manufacturing and post-processing concerns for rapid manufacturing and the different costs that are associated with manufacturing any component. So, in the first place, let us see why the need to post-process arise. So, since we are performing a kind of step as a post-processing, so why is it needed altogether? So, in additive manufacturing, we can develop products from basic design of the component and improve to optimize the iterative product development time. So, in additive manufacturing, we have a basic design of the component, and we can optimize the iterative product development time. Okay, that is when that whenever you go to a manufacturing process or a batch production, so you need to manufacture a certain product in repeated number of times. So how that design of a component can be optimized to perform iterative operations on them or a number of production operations on them so as to optimize the development time of the object. So, in additive manufacturing, the need for post-processing arises because of three major reasons. First is the staircase effect, second is the surface quality, and third is the dimensional accuracy. So now, what is the staircase effect altogether? So in additive manufacturing processes, as you all remember, it is a layer-wise process. Okay, this is a layer-wise process. So what happens is whenever you go on to print a geometry, say a cube, it will always be discretized into number of layers. So suppose this. Now, when this side are not straight or vertical, instead they are inclined at an angle. Suppose now this is your geometry, kind of a parallelopiped. Now, when this geometry will be discretized, so when a single layer is being drawn, so it will be discretized in this manner. Okay. So you see here a kind of stairs are formed. So this isn't a smooth surface. See, these are all the stairs. Stairs on a slant surface. Alright. So whenever this kind of inclined geometry is encountered, there are formation of stairs, and this is known as the staircase effect. So a stair-like formation because of inclination in geometry okay, so this is stair like formation during discretization because of inclination in geometry. Now because of this, you see this isn't a smooth surface, instead this has induced some kind of surface roughness. All right, so if this staircase effect would not have been there, there would have not been any kind of surface roughness. Then your surface quality, because of the limitations of the resolution of different additive manufacturing or rapid manufacturing processes, the surface quality is compromised because it varies from sometimes from microns to some millimeter in some cases. So this needs to be controlled, and this depends on a variety of parameters like the process parameters, different technologies of additive manufacturing, etc. And the third is the dimensional accuracy. Okay, so there are always some kind of tolerances and limits which are specific to the machine, which need to be taken care of while developing any kind of a product. So these account for the dimensional accuracies. Now let us go through the defects in rapid manufacturing parts briefly. So there are some 4 to 5 defects for majorly. So first we'll study about the porosity defect, which is a very common kind of defect in most of the additively manufactured parts. And because why this occurs, because of the binding mechanism are driven by temperature changes. Okay, so in additive manufacturing, all the binding mechanisms are driven by temperature changes. Binding mechanism refers to the solidification process. Okay, so be it a powder based process, bed process, or fused deposition modeling or binder jetting. So there are always some temperature changes associated with those, and the gravity and capillary forces, which can lead to porosity. Okay, so you have different kinds of pores. First are the irregular pores, and the second are the spherical pores. So what are irregular pores? They are formed due to shrinkage. Whenever there is shrinkage, so suppose this is your part, and there is larger shrinkage in this region and lower shrinkage in this region. So there will be some irregularity in the pore shape, or there will be a pore here, like that. And this happens occurs because of lack of binding or fusion or material shortage, lack of binding or fusion or melting, okay, or material feeds shortage. Okay, so whenever there is a part, suppose this is your part, this cube is your part. Now these two layers are not able to fuse together or have not melted completely, so there will be certain pores left at the interface. Okay, now another is the spherical pores, which are commonly formed due to trapped gases which are trapped in bubbles or Marignon turbulence in the melt region. or material evaporation, which is very common in processes associated with high temperatures, which is for high temperature processes, etc. So these are some of the factors which causes spherical pores. So we need to control porosity to control the properties of the object. Now another kind of defects are cracks. Cracks is a serious problem in a majority of the additive manufacturing processes, and they are formed due to several reasons. One of the major reasons for these cracks is because of thermal stresses and uneven cooling. So whenever a second layer is being laid over the first layer, there are some compressive and tensile stresses. So suppose this is your object. So this was your previously deposited layer. So it had, and this is your fresh layer, and this is your previous layer. So when you deposit this fresh layer, which is at a higher temperature, this is at higher temperature comparatively to this previous layer. So because of these thermal gradient, there are compressive stresses in the lower layer and tensile stresses in the upper layer, which causes these different layers to expand and contract and hence develop cracks. Okay, so this was because of thermal stresses. Another is uneven cooling or rapid cooling. So what happens is different sections of a component cool at different rates. Okay, so suppose there are these two layers only. Okay, layer 1, layer 2. So this cools at a faster rate. This is this one, faster cooling, and this one shows a slower cooling. Now because of faster cooling, this bottom layer will try to shrink faster, and this above layer will develop resistance to this shrinkage. So and hence in this process of a tug and war like situation, there will be cracks developed at this interface. Okay, now another reason is compositional segregation and drying and shrinkage of a binder material. Okay, so or shrinkage of binder material. So whenever there is compositional segregation, like there are different phases present in a component, then what will happen is different phases have different properties and different heating and cooling cycles. And in such a situation, because of the difference in cooling cycles and heating cycles and difference in thermal stresses, degree of thermal stresses, there will be cracks developed in the component. Now, next kind of defect is distortion and delamination. Okay, so these are the defects that are caused because of the volumetric change, because of the changes caused in the material volume. Okay, they originate from the stresses caused by changes in material volume. Okay, so ultimately everything is associated with these high temperature, high energies, and these thermal stresses and cooling and heating rates. So because of the difference in cooling and heating rates in this laminated structures only, like I had explained before, so when one layer cools faster and the other is cooling at a slower rate, what can happen is it can turn into bended shape. It can bend like this. This is warpage. And okay, and they can even delaminate from each other. Okay, when delaminate from between, that is the interface can break from somewhere in between. So that is distortion or delamination. Okay. So these are caused because of large thermal gradients within the component. Large thermal gradients within the additively manufactured component. Now another is poor surface finish. So poor surface finish originates from different factors such as the staircase effect. Like I had told you, because of the inclination in the geometries or the object surfaces, so when that particular object is discretized in the form of layers, the outer surface is formed in kind of stairs. So this will be the how the layers will be discretized. So at this particular edge, there is these stair-like formations. These are your stair-like formations. Now, because of these, you have surface roughness. Now, what factors are responsible for these, or what can be the remedies? So, layer thickness. What are the factors that are associated with this staircase effect are layer thickness. So higher the layer thickness, higher will be the surface roughness because of staircase effect. So imagine this is one layer, and if you have another layer in which you have smaller surface thickness, so it will be like this. In this you have smaller layer thickness. So if you observe keenly, here the surface roughness has reduced. So you can say smaller surface thickness, smaller layer thickness reduces surface roughness. So compare the layer thickness in these two and compare the surface roughness qualitatively. You will find lower surface roughness in this. Okay. Now let us come to build orientation. So we can play with the build orientation to minimize the inclination of the parts. Okay, so if there are any inclined geometries, we can just orient them in such a way in the build platform that they are almost vertical, or they have reduced inclination of the surfaces. And then there is coarse bead deposit beads. So coarser the beads, higher will be the surface roughness. Now another factor for poor surface finish is low tool precision. Okay, so lower the precision, higher will be the surface roughness. Okay, and then there are surface tension and balling effect. So this balling effect is majorly associated with the powder bed processes. Okay. This is majorly associated with powder bed processes, wherein because of the surface tension effects, your melt tends to form spherical balls. Because of surface tension, the melt pool doesn't wet the substrate. Instead, it forms spherical balls of melt. And this is what is balling effect, and this increases the surface roughness. Now, last of the defect is chemical degradation and oxidation. So it is dependent on the atmospheric conditions, because in high temperature processes there is chances of oxidation, or some elements has a higher affinity towards oxygen, like magnesium has a highly exothermic reaction with oxygen. So it needs to be processed kind of in absence of oxygen. So it depends from material to material and how they behave with the atmospheric gases. And next is your processing parameters, wherein input energy and working temperature are major factors affecting the chemical degradation and oxidation. So at higher temperatures, the metallic elements usually tend to form their oxides. So in order to optimize that or avoid the formation of oxides or metallic oxides, we need to have controlled atmospheric conditions as well as the controlled processing parameters. Now, what are the issues that are concerned specifically with the metal parts, metal rapid manufactured parts? So, their attraction for atmospheric conditions, like I had been mentioning about this Mg. So, metals have higher attraction for atmospheric oxygen. Okay, so they tend to immediately form these oxides at higher temperatures. And as you know, these powder based processes, specifically processes having use of lasers, they are very high temperature processes. So these metals tend to oxidize at such high temperatures in presence of oxygen. Now, high reflectivity and thermal conductivity. So, all metals are associated with high thermal conductivity. So, this hampers the laser absorption. Okay. So, this hampers the absorption of laser energy, which in turn hampers the formation of melt pools, etc. Because higher the thermal conductivity, the more the higher amount of heat will be conducted away, and higher the reflectivity, higher will be the amount of heat that is reflected away from the powder. So there is nothing that would be available to heat the powder. And last is the residual stresses, so which are the presence of these compressive and tensile stresses in consecutive layers. So these are compressive stresses in the layers below and tensile stresses in the top layers. So we need to minimize or eliminate these residual stresses for better part performance. So now every material or every component having any kind of overhangs requires support. Now there are two kinds of supports. One are the natural supports and the other is the synthetic support. So what are natural supports? So, in processes where the part being built is fully encapsulated in the build material, that are the natural supports. Okay, wherein you do not need any secondary material or any other material to produce the supports. Okay, whatever your build material is, your part is encapsulated in there. That is natural support. Okay. Processes which provide natural support are primarily powder based processes, and sheet based processes. So it is there in processes where the part being built is fully contained in the build material. So like in powder bed processes, the part whatever is being built, it remains in the powder. Okay, it is not solidifying the powder to provide support, nor it is using any extra material to provide support. Instead, that loose powder is in itself providing the support. So such are known as natural supports. Okay, so in such a case, what you need to do is what you need to remove the supports. Okay, these supports can simply be removed by the use of brushes. So how do you remove the support or do the post processing? So use of brushes. So you can simply just brush off the loose powder that is clinging onto your component, or you can use compressed air or pressurized air. So to blow away the loose powders from your component, or you can also have used brushes, you have used pressure compressed air or pressurized air, or you can use light bead blasting. So like there is sand blasting or shot peening, wherein you just hammer your component with the small balls or sand. There is light bead blasting, where light beads are blasted onto your component to remove the loosely adhered parts. Okay, to remove the powder that is loosely adhered to it. Now in let us move to synthetic supports. Okay, so these are for the processes which do not naturally support the parts. Okay, processes which do not naturally support parts require synthetic supports for overhanging features. Okay, so in such a case you need some secondary material to provide support. Okay, or from the build material itself. So supports are made either from a secondary material or from the build material itself. So like in FDM based process, suppose you are using PLA, so that PLA filament in itself is used to form the supports. You do not need or that bed cannot in itself support the overhangs. Okay. Now your orientation of the part significantly affects how the supports are to be generated. Okay, now there are different like water soluble supports, water soluble supports. So these are a secondary material and they can be dissolved in water after you take them out. Or there are supports, the supports that are from the build material, they need to be broken off, or that suppose there are extra supports in the form of metallic parts, so they need to be machined, etc. So they need to be taken out by some kind of chemical or mechanical methods. Now how you can improve your surface texture. We have seen the defects and we have seen how there are supports. Now when there are defects, they cause surface roughness and poor surface finish, and these supports also, they also leave certain marks on the surface of your components when these supports are taken off. So how you can improve the surface texture or surface roughness? Let us look into some of the methods. So it depends on how surface finish you want, or what is the desired surface finish, how much fine surface you require. So one method is painting, which would like applying paint on the surfaces. This would seal all kind of porosities, and it would also smoothen the staircase effect by the viscous forces, because since paint is a highly viscous material, that material will stay in the cases formed by the stair. So let me show. So in here, your that paint will just go and sit in these spaces, and it will just form a smooth surface. Okay, because of the viscous forces, it will just stay here. Now another one is, there are some automated techniques that are available for surface texture improvement. One is tumbling for external features, that is for finishing the external features. Here you put your component in a tumbler. Component is put in a tumbler, and that tumbler is rotated with a powder, and certain powders or abrasive powders are filled in there, and certain abrasive or finishing powders are filled. And then the tumbler is rotated to finish all kind of external features. Now abrasive flow machining is used for internal features finishing. So in this, your this abrasive particles are mixed in a fluid medium, say water usually, and are made to flow at high speeds through the internal channels and cavities. Okay, and this is then responsible for finishing these internal features of any component. Okay, now how you can improve the accuracies? So the tolerances for any machine varies from sub-microns to some millimeters, and larger the build volume, higher will be your build speed. So the accuracy will be degraded. So whenever you need higher accuracies, you need to slower down your speed for better accuracies. So we need to slower down the build speed for better accuracy, as the machine will get higher time to accurately machine the component. Now particularly in beam deposition kind of a process, the beams that are the slowest and the most accurate one has accuracies approaching few microns. Okay, when the beam has a slow deposition rate and it moves very slowly, melting and fusing each part, their accuracies are very good, to few microns. But when you have large bulk machines which work at a higher deposition rate, they have low accuracy of few mm only. Okay. Now, what are the error sources? Error sources come from positioning and indexing limitation of the machine architecture, and they are different in X, Y, and Z directions. Since the motions or the step size of X, Y, and Z directions are different, your accuracies are also different in the three directions. And another one is shrinkage and distortion. Say suppose you want to print say cube of 2 mm, 2 centimeter by 2 centimeter, 2 mm by 2 mm, say. Okay, and this has an accuracy of plus minus zero point 0.2 mm. So, or sorry, uh, there is a shrinkage of say 0.5 mm when it cools down. So what you will be left with a part of 1.5 mm by 1.5 mm. So you need to account for these shrinkages whenever you are modeling any component. Now, model pre-processing, accuracy is influenced by part orientation and position within the build chamber. So it is very important to control how your part is oriented in the build chamber, and scaling to compensate for shrinkage, like I told you, that you need to account for the shrinkage whenever you are modeling. So if you know there is 0.5 mm of shrinkage and you need a component of 2 mm, so you will initially design it for 2.5 mm, so that after a shrinkage of 0.5 mm, you will have it in the desired number of 2 mm. Another is machine strategy, wherein you will be adopting adaptive raster milling, or your sharp edge contour machining. Then aesthetics improvement, you can improve the aesthetics by having paints, by painting the surface, improving the surface finish, providing colors, different colors to the component, by plating the component with any other material. And then the last is property enhancement using non-thermal and thermal techniques. So for non-thermal techniques, maybe you can use UV exposure in case of photopolymerization reaction, and longer exposure to UVs will strengthen the component and give you better mechanical properties. And then there are thermal techniques to eliminate residual stresses and further enhance the properties. Now let us move to the second part of the week's content, that is product costing for rapid manufacturing parts. So first is the direct labor cost plus materials cost. So the direct labor cost is the cost associated with the labor. Okay, so there will be certain people operating the machine who are putting in their time every day for your component manufacture. So they need to be paid certain wages. So that comes under your direct labor cost. And next is your materials cost, which is the cost of the direct material, which is evident in the component. So for example, you have developed this hollow cylinder. So this is your hollow cylinder. Okay. Now the amount of material that is visible in the final product the cost of that and the cost of the labor associated with manufacturing this. This forms your prime or the operational cost. Okay, this doesn't include the material that has been removed. To make a note, does not include the cost of removed material. So this is then compensated in factory out overhead, which contains the cost of indirect material. Indirect material is the amount of material that is not known by the user, or the amount of material that was initially taken to develop the component. Okay, so this contains the cost of this removed material, and it can contain the cost of tools, fixtures, okay, etc. And then it contains the cost of your rent, insurance, factory maintenance, okay, any kind of extra cost. Okay, and then this is your prime cost, that is part 1. Now altogether this forms the cost of the goods manufactured, or the total manufacturing cost. So you can see the total manufacturing cost is majorly consisting of 4 parts, which is the recurring labor cost or the variable labor cost, the cost that you need to give to the labor. So it depends on the number of, it depends upon the production volume. Manufacturing cost per unit. Recurring material cost, that is variable, that is again variable material cost, or the cost of the raw material. Next is allocation of non-recurring tooling. Non-recurring tooling is the cost for the overheads that are required for only a few times, maybe your tools, fixtures, etc. And then is the capital cost, which is the cost associated with the equipment. Now let us check certain concepts. So this is your fixed cost. So this, for traditional manufacturing, this is the fixed cost for traditional manufacturing. So this contains the cost of your rents, insurance, electricity bills, salaries, etc. Whatever is fixed. Okay. Then there is a variable cost, which is of labor, material, servicing, etc., which varies from time to time and upon the production volume. So the sum of these fixed cost and variable cost gives you the total cost. So fixed cost plus variable cost is equals to the total cost. Okay, so this is for traditional manufacturing. Now suppose you have set your selling price as this green line. So this point becomes your break even point, BEP. Break even point. That is, it is after this point that you will be able to generate revenue. Okay. After this point, profit or revenue is generated. All right. So this is your profit. Now, in case of additive manufacturing, your fixed cost increases. So your fixed cost will increase, like it will go to here. Fixed cost for additive manufacturing. This is associated with the higher cost of the equipment. Okay, so AM machines, as in specialized machines, they have certain higher costs, but your variable cost reduces. Okay, so your variable cost will be like something like this. So suppose this is your variable cost. So this is your variable cost for AM. Now, what will be your total cost? The sum of these. So this will be your total cost. So let me draw variable cost again. So this was your fixed cost. So this is your variable cost for AM. So this becomes your total cost for additive manufacturing. Now you see your break-even point has reduced to this one. Okay, so this is your BEP now. So what is there? You will start to generate revenue earlier, and your revenue will be higher in amount as well. So this is your revenue now. So this is your revenue because of additive manufacturing. Okay, so this is how the costs are affected with the introduction of additive manufacturing. Now let us take into account some more features. Now how it is affected by the production volume. So for traditional manufacturing, your per unit cost is higher if your quantity is small, okay, and it is lower when your quantity is really high. So because here you use general purpose machines and here you use special purpose machines which are specifically designed for batch production. But with any additive manufacturing, there is not much change in per unit cost, so it remains more or less the same. So you can say when your production volume is lower in this area, your additive manufacturing cost is lower. So this is lower till here. So you can say in this region, additive manufacturing is better. But when you move to this region ahead of this, you see the manufacturing cost or per unit cost with traditional manufacturing is lower. So hence in this region you say traditional manufacturing is better. Now we come to the complexity in design. So this is your additive manufacturing and this is your traditional manufacturing. So now here this is your simpler designs, and as you move here these are your complex designs, and complexity is increasing in this direction, increasing complexity. So you see, in case of simple designs, your traditional manufacturing is better. But as you move towards more complex designs, additive manufacturing proves to be a better technique in terms of per unit cost of the manufactured component. So you need to optimize with the design complexity, production volume, and the price. To select either traditional manufacturing will be a goal or additive manufacturing will be a goal. And also there are certain models the cost model and the build volume model that can be used to check which manufacturing technique is better, or how additive manufacturing cost will be affecting you in terms of your business. Okay, so in this week's we studied about the post processing techniques. So why is there a need of post processing? Because of the staircase effect, which causes surface roughness, because of the problems of surface finish, and because of the problems of dimensional accuracy. Then we saw certain defects that are present in additively manufactured parts, which are namely as porosity, cracks, then your delamination or distortion. Uh, and then we saw uh, the other defects were poor surface finish and chemical degradation and oxidation. Then we studied what are the issues in metal additive manufactured parts. They are their affinity towards atmospheric conditions, their conductive and reflective nature, and the generation of residual stresses. Then we move to the supports materials, the natural supports and the synthetic supports, how they are removed, and how we can work on the improvement of surface texture, the aesthetics, the accuracies, etc. And then we saw the product costing, wherein we saw what consists of the operational cost, what consists of the manufacturing cost, how the manufacturing cost varies, and what is the break-even point, how it is affected with the introduction of additive manufacturing, and how we need to optimize the costings based on the quantity, the production volume, and complexities in design. So we'll continue with another set of lectures in the next week. But for this week, now let us focus on some of the sample problems. So we'll be solving 10 sample problems. So question 1, additive manufacturing technique helps to develop a product from the basic design of the component and to optimize the iterative product development time. True or false? So, in additive manufacturing, we can make a product from basic design. This is true. And does it help us to optimize the iterative product development time? Yes, it does. So, the answer is true. Now, how it does? So, it helps us to optimize the product development time by optimizing various process parameters like the part orientations, the build speeds, layer thickness, raster strategy, etc. And there are many more factors that go on to affect the product development time. Now, question 2. Dash occurs when the liquid material fails to wet the underlying substrate, thus spheroidizing the liquid. Wetting, contamination, balling, or none of these. So, whenever your laser hits your powder bed, there is the formation of melt pool. Okay, melt pool forms because of high temperatures caused by high energies of laser. For example, in powder based processes specifically. Now, sometimes what happens is, suppose this is your substrate and this is your melt pool. Okay, now this isn't able to wet this. So what will happen, it will start to these melt pool will start to come closer to itself, so it will kind of make a spherical globule. Okay, so because of the surface tension forces. Okay, it avoids interaction with the substrate as much as possible. That is, it doesn't wet the substrate. So hence it makes a ball-like structure, which is the sphere of the liquid, and hence this effect is known as balling. Now, next question. Contaminations can reduce the wetting degree. True or false? Yes, it is true. It is because of these contaminations only that there is lesser wetting. Okay, and hence you have this balling effect. Now, question 4. Porosity is a common defect in additively manufactured products. True or false? Yes, this is true. And we had seen there are different kinds of pores, which are your irregular pores and your spherical pores. Your spherical pores are generated because of the trapped gases or Marignoni effect in the melt pool. And your irregular pores are caused because of your shrinkage and unequal cooling and etc. So next question, which of the following give rise to cracking? Compositional segregation, shrinking of binder material, drying, or all of these? So the correct answer is all of these, since we have talked about how compositional segregation causes cracking and then shrinkage of binder materials. So suppose you have two different materials, one is your main component and another is your binder material, which is in between these. So now if your binder material shrinks and your main component doesn't shrink, then there will be a development of crack. And uneven and drying also causes cracks, like you have seen when the soil dries to a very high extent, there are cracks on the surface. So moving on to next question. Poor surface finish originates from factors such as staircase effect. True or false? True. So we had talked how inclined surfaces like these so causes staircase effect. So this is your staircase. Suppose this had been your component. So because of zero inclination here, there is no staircase, but because of an average inclination, there is inclination in geometry. There are staircases generated. So these are your stairs. And this leads to, has caused surface roughness or poor surface finish. Next question. In rapid manufactured parts, processing parameters such as higher energy input or working temperature can also increase chemical degradation and oxidation. True or false? This is true. Whenever your temperatures go higher, the tendency of specifically of metals to oxidize becomes higher. Okay, so the tendency of metals to form oxides becomes higher at higher working temperatures. Okay, and formation of oxides leads to degradation. And also, as your energy input increases, your temperatures in the print bed also increases, leading to the similar effect as that of higher working temperature on the oxidation and chemical degradation. Now, question 8. Processes which provide natural supports are primarily powder-based processes and sheet-based processes. True or false? Answer is true. The loose powder in the powder bed and the stacked sequence of sheets provide the necessary support to the overhang parts. Okay. So in such a case, you do not require any kind of secondary material to provide the support. Question 9. Which of the following can be used to remove the loosely adhered powder? Brushes, compressed air, light bead blasting, or all of these? So all of these can be used to remove the loosely adhered powder. So you can simply either brush off the powder, okay, like you brush off the dust from any kind of clothes or walls, or you can use compressed air, so that is a highly pressurized air that is blown over the component, and because of the pressure of the air, the loosely adhered powders tend to flow away. And light bead blasting, you can blast the component in presence of light beads, which will force the loosely adhered powder particles to leave the component surface. Last question. In most cases, parts made using binder printing are malleable and strong. So this is false. Okay, so I hope all of you have understood and are clear with the concepts that were there in today's lecture. If anyone has any questions, you can raise them up. Okay, so this lecture video will be available to you through YouTube link, and these slides will be available through Google Drive link. Hope to see you in next week's lecture as well. Thank you all. So I'll wrap up this meeting. Thanks everyone.